Welcome again, everyone. In this video, we're going to explore analog to digital converters, or ADCs, a supercritical component in edge devices. An ADC is a device that converts analog signals into a digital signal, which your computer or microcontroller can then process. Think of it as translating a smoothly varying temperature reading into a format that your digital thermostat can understand and act upon. Key to understanding ADCs is the concept of resolution. The resolution of an ADC tells us how finely it can divide the input voltage range into different levels. For instance, a 10-bit ADC divides the voltage into 2 to the power of 10, or 1024 unique levels. As you will see shortly, higher the resolution, the better the analog to digital conversion. This resolution, along with the resolution of the sensor, impacts the precision of your digital readings. And you will see this shortly when we look at an example. Coming to the working of an ADC, it is actually pretty straightforward. First, the resolution or the number of bits and the reference voltage are used to calculate the step size using the formula shown. Once the step size is known, in the next step, the input voltage received from the sensor is compared to the step size and simply assigned a unique digital code. Let's see how this works in practice. For an Arduino Nano, the reference voltage is 3.3 volts, and the ADC resolution is 12-bit, according to the datasheet. Using the formula, our step size, therefore, comes out to be approximately 0.8 millivolts. And so, any input sensor voltage between 0 and 0.8 millivolts will be assigned the digital code 00000000000, or 12 zeros. A voltage between 0.8 millivolts and 1.6 millivolts would be assigned the code 00000000001, or 11 zeros and a 1, and so on. Neat, isn't it? We stated a little bit earlier that higher the resolution, the better. Now that we understand the working of an ADC, let's see why that's the case. Taking our current example, any value between 0.8 millivolts and 1.6 millivolts will be given a unique digital code. But that's a wide range. The same digital code would be generated whether the input sensor voltage was 0.85 millivolts or 1.55 millivolts. When this digital code is converted back to a value to be used in the code, or for making machine learning predictions, it will lead to loss of accuracy as the computer won't know the difference. That is, it wouldn't know whether the initial value was 0.85 millivolts or 1.55 millivolts. Now, if we were to increase the number of bits, the n in the formula, so that the step size became 0.1 millivolts, then in that case, only values between 0.8 millivolts and 0.9 millivolts would have a unique code, and on converting back to a value, the error in judgment would be much lesser. Let's now include the sensor resolution in this example. If the resolution of a temperature sensor was 0.25, it would take readings like 10.25, 10.5, and so on. That is, any temperature value between 10.25 and 10.5 would be assigned one of these values. Let's also say that 10.25 corresponds to 1.55 millivolts. So, if the actual reading was 10.37 degrees, it would first be converted to 10.25 degrees, then to 1.55 millivolts, and then to a digital signal using the ADC. This digital signal, when converted back, could have a value much different from the actual value of 10.37. To summarize, the translation of an analog sensor value to digital value using ADCs, though not perfect, is still highly precise and allows devices in edge computing, like wearables and smart devices, to efficiently process real-world data and make smart decisions quickly and locally. Hope you enjoyed this video. In the next few videos, we will look at the different communication protocols that are used by external devices to communicate with the edge device. See you there!